Imagine discovering a machine that predicts the future with astonishing accuracy. Every time you test it, the machine works. Not occasionally, not most of the time, every single time. It correctly predicts outcomes with precision, unmatched by any invention in human history. Engineers build entire industries around it. Scientists trust it. Experiments confirm it again and again. Then someone asks a simple question: how does it actually work? And suddenly, nobody agrees on the answer. That may sound absurd, but it describes one of the strangest situations in modern science. Quantum mechanics is widely regarded as the most successful scientific theory ever developed. The smartphones in our pockets, the lasers in hospitals, the computer chips powering modern civilization, and countless other technologies exist because quantum mechanics predicts nature with extraordinary accuracy. By every practical measure, the theory is a triumph. Yet, hidden beneath that success lies an uncomfortable secret. Physicists still argue about what quantum mechanics is actually telling us about reality. This is not a minor disagreement. It concerns one of the most fundamental questions science can ask. What is really happening when a quantum event occurs? Most scientific theories eventually provide two things. They tell us what will happen, and they tell us why it happens. Newton's laws explain falling objects. Einstein's relativity explained gravity in a deeper way. Quantum mechanics is different. Its predictions are astonishingly successful, yet its underlying meaning remains deeply contested. For decades, physicists have used the theory to calculate outcomes with incredible precision, and yet many physicists remain uncomfortable, not because the theory fails, because it succeeds without fully explaining itself. The deeper researchers explore quantum mechanics, the more they encountered a strange tension. The equations seem to describe nature perfectly, but the reality behind those equations remain frustratingly unclear. Humanity may possess the most powerful predictive framework ever created, while still lacking agreement about what that framework says is happening beneath the surface. Why is a theory capable of explaining so much left some of the greatest scientific minds arguing over its most basic implications? To answer that, we must step into a world that behaves very differently from our everyday experience. A world where certainty gives way to possibility, and where the deepest mystery in quantum physics first begins to emerge.
The difficulty begins when we compare the quantum world to the world we experience every day. Look around you. A chair occupies a specific position. A book rests on a particular table. A light is either on or off. Everyday objects appear to possess definite properties, whether we are paying attention to them or not. The world feels solid, stable, and unambiguous. Quantum mechanics tells a different story. At extremely small scales, nature seems to follow rules that challenge this intuitive picture. Instead of describing a particle as being in one definite state, the mathematics often describes multiple possible states existing simultaneously. This idea is known as superposition. Unfortunately, the word itself can create confusion. Many people hear it and immediately imagine a particle physically splitting into multiple copies of itself. That is not necessarily what the mathematics says. What it says is that before measurement occurs, the system is described by a combination of possible outcomes, rather than a single definite one. A simple example helps. Imagine flipping a coin. In everyday life, the coin lands as either heads or tails. Even while spinning through the air, we assume it already possesses a specific physical state. If we knew enough information about the flip, we could theoretically predict the result. Quantum systems behave differently. Before measurement, the mathematics does not simply reflect our ignorance about the outcome. Instead, it treats multiple possible outcomes as part of the system's description itself. This distinction is crucial. In classical physics, uncertainty usually means we lack information. In quantum physics, uncertainty appears woven into the structure of the theory. That realization shocked many of the scientists who helped create quantum mechanics. The equations repeatedly suggested that nature does not always operate in the straightforward way common sense expects. Instead of following a single predetermined path, quantum systems evolve according to a range of possibilities. For decades, physicists have used mathematical objects called wave functions to describe this behavior. The wave function does not tell us which outcome will occur. Instead, it describes the probabilities associated with different outcomes. And remarkably, it works. Again and again. Experiments confirm the predictions with extraordinary precision. This is where the mystery begins to deepen, because the mathematics itself is not the problem. Physicists know how to calculate quantum probabilities. They know how to predict experimental results. The theory succeeds so consistently that there's little doubt about its practical power. The real puzzle lies elsewhere. What exactly do those possibilities represent? Are they merely mathematical tools? Do they describe something physically real? Do all possibilities somehow exist simultaneously? Or is the wave function simply a method for organizing information? Quantum mechanics does not provide a universally accepted answer. To see why this becomes so troubling, imagine applying a logic of superposition to larger objects. Suppose a quantum event determines whether a box contains a live cat or a dead cat. According to mathematics, before observation, the system can be described by multiple possible outcomes. This famous thought experiment, proposed by physicist Erwin Schrödinger, was never intended as a serious description of cats. It was designed to expose a problem. The equations seem comfortable describing possibilities. Reality appears to deliver definite outcomes. Somewhere between those two facts, a profound mystery emerges, because when we actually perform experiments, we never observe a blur of possibilities. We do not see objects existing in multiple contradictory states at once. We observe specific results. One detector clicks. One outcome appears. One event occurs. The mathematics describes many possibilities, yet experience reveals only one reality. And that creates a tension at the heart of quantum mechanics. The theory seems to evolve smoothly according to precise mathematical rules. But the moment a measurement occurs, the story changes. Possibilities appear to give way to a single outcome. The question is simple. How? Where does possibility end and reality begin? That question has haunted quantum physics from the beginning, and it leads directly to the deepest mystery in the entire theory. Because the equations describe the evolution of possibilities with remarkable clarity, but the transition from possibility to actuality remains one of the most debated problems in modern science. Up to this point, quantum mechanics seems strange but manageable. Particles are described by possibilities. Wave functions evolve according to mathematical rules. Probabilities replace certainty. Unusual, perhaps, but not necessarily mysterious. The real mystery appears when a measurement takes place. This is the point where quantum mechanics transitions from being merely counterintuitive to becoming genuinely puzzling. The equations governing a quantum system are remarkably clear. Given a wave function, physicists can calculate how it evolves through time. The process is smooth, continuous, and completely predictable. The mathematics follows precise rules. Then a measurement occurs, and suddenly something different seems to happen. Instead of multiple possibilities continuing to evolve, only one outcome appears. A detector records a specific result. A particle is found in one location. An instrument displays one value. Reality presents a single answer. The problem is that the standard equations do not clearly explain how this transition occurs. This issue is known as the measurement problem and has become one of the deepest unresolved questions in modern physics. To understand why, imagine a simple experiment. Suppose a quantum particle can be detected in two possible locations. Before measurement, the wave function describes both possibilities. Physicists can calculate the probability associated with each outcome with extraordinary precision. Everything works perfectly. Then, the measurement happens. The detector does not record both outcomes. It records one. The wave function appears to collapse from many possibilities into a single observed result. But what exactly caused that collapse? That is where the trouble begins. The mathematics describing the evolution of the wave function does not seem to contain a clear mechanism explaining why one possibility becomes reality while the others do not. For decades, physicists have been forced to confront an uncomfortable fact. Quantum mechanics tells us what will happen statistically. It does not clearly tell us what physically happens during measurement. This may sound like a technical issue, but its implications are enormous. Imagine reading a detective novel that perfectly describes every event leading up to the final chapter. Every clue is accounted for. Every character is explained. Every probability is calculated. Then, when the mystery is finally solved, the crucial page is missing. That is how many physicists view the measurement problem. The theory works. The predictions work. The calculations work. Yet something essential appears absent from the explanation. The difficulty becomes even more obvious when we ask a seemingly innocent question. What qualifies as a measurement? At first, the answer appears straightforward. A scientist observes an experiment. An instrument records data. A detector interacts with a particle. But where exactly should the boundary be drawn? Does measurement occur when a detector registers a signal? When information is stored? When a system interacts with its environment? Different interpretations provide different answers. And that is precisely the problem. There is no universally accepted solution. The deeper researchers investigate the issue, the harder it becomes to identify the exact moment when possibilities become a single observed reality. Some physicists argue that collapse is a real physical process. Others believe collapse never actually occurs at all. Still others suggest that the apparent collapse emerges from interactions between quantum systems and their environments. The remarkable fact is that these competing views often produce the same experimental predictions. This is what makes the measurement problem so frustrating. The mystery does not arise because experiments disagree with quantum mechanics. The mystery arises because quantum mechanics agrees with experiments while leaving fundamental questions unanswered. Imagine watching a movie without understanding how the projector works. You can follow the story. You can predict what happens next. You can enjoy the experience. Yet a crucial part of the mechanism remains hidden. The measurement problem creates a similar situation in physics. Scientists possess a mathematical framework capable of extraordinary predictive power. Yet when they ask why one possibility becomes the outcome we observe, the answers become uncertain. And uncertainty of this kind is unusual in science. Most unresolved scientific questions concern things we have not yet observed. The measurement problem is different. It concerns something happening in every quantum experiment ever performed. Every successful measurement quietly relies on a process that remains incompletely understood. That is why many physicists regard this as more than a philosophical puzzle. It strikes at the heart of what a scientific theory is supposed to provide. A theory should not merely predict outcomes. It should explain them. Quantum mechanics predicts outcomes better than any theory in history. Yet nearly a century after its creation, physicists still debate what actually happens when possibility becomes reality. And that debate has produced one of the most fascinating intellectual battles in all of science. Because if the theory itself does not provide a universally accepted explanation, then perhaps the explanation lies elsewhere. Over the decades, some of the greatest scientific minds have proposed radically different solutions, each attempting to solve the same mystery while arriving at dramatically different visions of nature itself. Once physicists recognize a measurement problem, they naturally attempted to solve it. At first, many assumed the answer would arrive quickly. After all, quantum mechanics was producing astonishingly accurate predictions. Surely the conceptual gaps would disappear as the theory matured. Instead, the opposite happened. The deeper researchers examined the problem, the more competing explanations emerged. Rather than converging toward a single answer, physics found itself divided into multiple camps, each offering a different account of what happens during measurement. And remarkably, many of these explanations fit the same experimental evidence. The oldest and most influential approach is often called the Copenhagen interpretation. According to this view, the wave function provides a complete description of a quantum system before measurement. When a measurement occurs, the wave function collapses into a definite outcome. For decades, this interpretation became the practical working framework for generations of physicists. It was successful, it was useful, but it left an uncomfortable question unanswered. What actually causes a collapse? The Copenhagen interpretation describes the process, but many critics argue that it does not fully explain the mechanism behind it. The collapse appears in the story. Its origin remains unclear. Not everyone was satisfied with that. Some physicists believe the problem was not with the mathematics, but with the idea of collapse itself. Perhaps They argued collapse never occurs at all. This idea eventually evolved into one of the most famous alternatives, the many worlds interpretation. According to this proposal, the wave function never collapses. Every possible outcome described by quantum mechanics continues to exist. When a measurement takes place, reality effectively branches into multiple versions corresponding to different outcomes. The attraction of this idea is obvious. The mathematics remain smooth and consistent. No special collapse mechanism is required. Yet the cost is extraordinary. Reality becomes vastly larger and more complex than ordinary intuition suggests. Every quantum event contributes to an ever-growing structure of possibilities. For some physicists, this is an elegant solution. For others, it feels deeply unsatisfying. The debate continues. Then there are objective collapse theories. These approaches take a different path. Instead of treating collapse as an apparent effect or denying its existence altogether, they propose that collapse is a genuine physical process occurring within nature itself. In these models, quantum systems can remain in superposition only up to certain limits. Beyond those limits, the wave function spontaneously collapses into a definite state. This idea offers something many physicists find appealing. It turns collapse from an abstract rule into a physical event. But it introduces new challenges. What triggers the collapse? How often does it occur? Can the process be experimentally verified? Researchers continue searching for answers. Another important approach involves a concept known as decoherence. Decoherence studies how quantum systems interact with their environments. As those interactions increase, the system becomes entangled with countless surrounding particles. Quantum effects that were once obvious become effectively hidden from observation. This framework has successfully explained many aspects of why the everyday world appears classical rather than quantum. It is an important breakthrough. Yet many physicists argue that decoherence alone does not completely solve the measurement problem. It explains why certain outcomes become difficult to observe, but questions remain about why a specific outcome ultimately appears. The mystery persists. What makes the situation so unusual is that science rarely finds itself here. Normally, competing explanations are tested against one another until weaker ideas are discarded. Evidence gradually narrows the possibilities. Quantum mechanics has resisted that pattern. Different interpretations often generate the same observable predictions. Experiments confirm the mathematics, but they do not always reveal which interpretation is correct. The result is a scientific landscape unlike almost any other. Brilliant physicists can examine the same equations, the same experiments, and the same evidence while arriving at radically different conclusions about what is happening beneath the surface. Some see collapse. Some see branching realities. Some see hidden physical processes. Some see environmental interactions, creating the appearance of collapse. Each approach resolves certain difficulties. Each creates new ones. And after nearly a century of debate, no interpretation has achieved universal acceptance. This is why the measurement problem remains so important. The issue is not that quantum mechanics lacks predictive power. Few scientific theories have ever been more successful. The issue is that success has not produced consensus. Physics possesses extraordinary answers, yet it still struggles with the question behind those answers. And perhaps that is the most remarkable aspect of the entire story. The greatest mystery in quantum mechanics is not hidden in a distant galaxy or buried inside an undiscovered particle. It exists at the very point where the theory meets observation, a place studied for generations, tested countless times, and still not fully understood, which raises a deeper question. What does it mean when science can predict reality with astonishing accuracy while remaining uncertain about what reality itself is doing underneath? Most scientific mysteries eventually follow a familiar pattern. At first, researchers disagree. Competing explanations emerge. New experiments are performed. Better evidence accumulates. Over time, uncertainty shrinks. The scientific community moves toward consensus. The measurement problem has stubbornly refused to follow that path. For nearly a century, physicists have debated the same fundamental question. Quantum mechanics predicts experimental outcomes with extraordinary precision. The mathematics works. The technology works. The evidence works. Yet agreement remains elusive. That alone makes this mystery remarkable. Usually, unresolved questions in physics involve things we have not yet observed. Scientists search for new particles, investigate distant galaxies, or explore extreme conditions beyond current experimental reach. The measurement problem is different. It concerns a process occurring in every quantum experiment ever performed. The mystery is not hidden. It is everywhere. Every time a detector records a result, every time a quantum event produces a definite outcome, the same conceptual puzzle quietly reappears. The theory successfully predicts what we will observe, but the deeper explanation remains contested, and that reveals something important about science itself. People often imagine science as a collection of answers. In reality, science is a process of understanding. Sometimes those two things advance together. Sometimes they do not. Quantum mechanics represents one of the rare cases where predictive success has outpaced conceptual clarity. Humanity can calculate quantum phenomena with astonishing accuracy. Engineers routinely use principles derived from the theory to build technologies that power modern civilization. Entire industries depend upon equations whose predictions have been verified countless times. Yet the meaning behind those equations remains the subject of ongoing debate. That situation can feel uncomfortable because it challenges a common assumption. We tend to believe that if something works, we must understand it completely. History suggests otherwise. People successfully navigated oceans long before understanding plate tectonics. They used fire long before understanding chemistry. They observed gravity long before understanding space-time. Practical success often arrives before complete explanation. Quantum mechanics may represent the most dramatic example of this pattern. The theory works so well that some physicists consider interpretational questions secondary. Others argue that the lack of consensus points towards something fundamentally incomplete in our understanding. Both perspectives continue to influence modern research. What makes the debate so enduring is that every proposed solution seems to solve one problem while creating another. Collapse theories explain definite outcomes, but introduce new mechanisms. Many worlds preserves mathematical consistency, but dramatically expands the structure of reality. Decoherence explains the emergence of classical behavior, yet leaves deeper questions unresolved. Each approach illuminates part of the mystery. None has ended it. And perhaps that is why the measurement problem continues to fascinate scientists, philosophers, and curious observers alike. It occupies a rare position at the intersection of mathematics, experiment, and explanation. It forces us to confront a distinction that is easy to overlook. Knowing how nature behaves is not always the same as knowing why it behaves that way. That distinction is the uncomfortable truth at the heart of quantum mechanics. The theory has transformed our understanding of the physical world. It has survived every major experimental challenge. It has become one of the greatest intellectual achievements in human history. Yet beneath that success remains a question that refuses to disappear. What exactly happens when possibility becomes reality? After a century of investigation, humanity still does not possess a universally accepted answer. And that may be the strangest part of all. The deepest mystery in quantum mechanics is not that the theory fails. It is that the theory succeeds so brilliantly, while leaving one of its most fundamental questions unresolved. We may have discovered the most powerful predictive framework ever created, and yet the moment where prediction becomes reality remains one of the greatest unanswered questions in all of science.